Hello and welcome back. So we have been talking about strain aging in last couple of lectures, and in the previous lecture we started discussing about dynamic strain aging. All right, so this is what we discussed in the last class, the Penning theory of dynamic strain aging. Okay, so what he did, he first constructed this plot between the flow stress and the strain rate. Okay, so that's what you can see over here, right? So instead of using a stress strain diagram, he used this particular plot to develop this theory and explain this kind of serrations which appear in the stress strain diagram of a material which goes through the dynamic strain aging. Okay, so what it did is, he said that first of all, you can consider the flow stress to be, consisting of these two parts. One coming from the strain hardening, and other, of course, is the strain rate dependent stress. So that's about the strain rate hardening, right? So if you now differentiate this particular equation with respect to the time t, then you would get this particular equation over here, right? So this is the strain hardening component, as I said, and this one is the strain rate hardening, right? Because that is what right now we are talking about as to how the stress would vary as you change the strain rate. Okay, so that's your strain rate hardening component. Okay, so if you now see this particular plot over here, you have a maximum at point A and a minimum at point B, right? Because within this range, from here to here, this is the strain rate range in which the dynamic strain aging can occur, right? So the moment you come to that particular range, the stress will go down as the strain rate increases, and as you come out from that range, the stress will again rise. Okay, so that is why you have this maximum and the minimum at point A and B respectively. Okay, so that means we can say that at point A and B, the slope of this particular curve, that is this d sigma epsilon dot by d epsilon dot will be 0. And now if you put that over here in this equation which expresses the epsilon double dot, then you would see that at point A and B, when the denominator becomes 0, the epsilon double dot will tend to become infinity. And what it essentially means that the strain rate will make a jump immediately as it reaches point A or point B. Okay, so at point A, when it makes the strain rate jump, it comes to this particular point over here, right? But the stress over here is lower compared to the stress that you are supposed to get at the applied strain rate, and therefore this will try and come down to reach that particular stress corresponding to the applied strain rate. Okay, and that's when it has to pass through point B, and as it comes to point B, this will again become infinity. Epsilon double dot will become infinity, and therefore there will be one more strain rate jump over here coming to this particular point, but here it is lower compared to the stress corresponding to the applied strain rate, and therefore it will tend to rise following this path and again come back to point A, and same thing will happen all over again, and this cycle will repeat, giving rise to this kind of serrations. Okay, so that is how, with the help of this particular plot between sigma and epsilon dot, Penning explained these serrations occurring in the stress strain diagram. So moving on, what we can say now, if you want to summarize this effect DSA in one particular sentence, you can say that the strain rate sensitivity is negative when dynamic strain aging occurs, right? We know the relationship between strain rate and the stress. It is related to this Powell law equation. So when dynamic strain aging occurs, we have seen that the stress comes down, right? So if you take the slope of this curve that you obtain by plotting this particular equation, that is going to be negative, and that is what is actually your strain rate sensitivity, right? Rate of change of stress with respect to strain rate. And since this is a Powell law equation, we will have dln epsilon dot in the denominator, right? So this is your strain rate sensitivity, or SRS in short, okay? So this will be negative when DSA occurs, and under normal conditions, when there is no DSA, then this is going to be positive, as we know, looking at this particular equation. Right? And in case of aluminium alloys, it occurs in certain alloys like aluminium, magnesium alloys. So here, magnesium is responsible for this particular phenomena as the solute atom. And we have seen a stress strain diagram of this particular alloy in the previous class as to how those serrations appear in the stress strain curve. And this can even happen at room temperature for this kind of alloys, okay? Now there are certain features of this serrated flow or these serrations that you have. First and foremost, as I have already told before, it occurs in a particular range of temperature and strain rate. For aluminium alloys, it can be from room temperature to certain elevated temperature. And talking about the strain rate, it can occur in the range of 10 to the power minus 5 to 10 to the power minus 2 per second, okay, in case of aluminium alloys. Number 2, for a given strain rate, it occurs at a certain temperature range and now again if you look at the aluminium alloys, this temperature range could be anything between minus 30 degrees Celsius to about 100 degrees Celsius, or maybe a little beyond that. Okay, so typically you can say within this range. So it covers the room temperature also, as I said before. And if the strain rate increases, the temperature for occurrence of serrated flow or dynamic strain aging also increases. Okay, so that's the second characteristics of this particular phenomena. Third, there are three types of serrations. And these are as follows. Type A, which typically looks like this. Type B, which appears as continuous serrations like this. And type C, which appears something like this. Okay, so these are the three types of serrations that might occur, and it depends on how that band in which the deformation is localized moves through the sample, right? So if you remember, we have discussed that the reason for this kind of inhomogeneous plastic deformation is the localization of plastic deformation in a band which propagates along the gauge length of the sample, right? So how that particular band propagates, depending on that, you will get one of these types of serrations, type A, type B, or type C. For example, type A occurs when the band moves continuously through the specimen. So here you could see that there are humps and valleys, right? Here and then again you have a valley, right? So it always consists of humps and valleys, as you could see from here. So these humps and valleys basically correspond to disappearance of a band and then initiation of a new band. Right? So you have one band disappearing and another new band initiating, right? So that is why you have these humps and valleys coming into the stress strain curve. Okay, so that is how the serrations are for type A, in which the band moves continuously through the specimen. B type serrations will come when the band hops from one position to another. From one position to adjacent one. And here one serration corresponds to one hop. Right, so you can see here distinct hops, distinct individual serrations, right, one after the other. So each of these correspond to one hop for the band. And in case of type C, there is no propagation as such. Rather, the band nucleates randomly on the specimen surface. Right, so the type of the serrations will depend on the behavior of the band, okay, as to how it will move through the sample. And the serration type changes from A to B to C with increasing temperature. And number 4, we can say that this changes from A to B to C with decrease in strain rate. These two features, 3 and 4, as to how these serration types change with temperature and strain rate can be depicted through a plot like this. Where you plot the strain rate as a function of temperature, and that gives you a straight line. Right, so this is the temperature range in which it occurs. Below this, there is no serrated flow, and above this also, there is no serrated flow. Okay, only within this range, the serrated flow or dynamic strain aging will occur. And the first thing that we noted is that as we increase the temperature, it changes from A to B to C. Okay, as we increase the temperature, that is how the serrations change. Okay, and you can also see that as you decrease the strain rate, you would have the same change from A to B to C. Okay, so with decreasing strain rate also, it changes as A to B to C. Number 5, this we have already seen that serrated flow is always associated with negative strain rate sensitivity. And there is a significant difference between steels and aluminium alloys as to when this dynamic strain aging will start. Okay, this is because of the fact that the alloying elements are of different types in steel and aluminium alloys. In steel, it is interstitial solute atoms that we are talking about, but in case of aluminium alloys, they are substitutional, as we know. So since it is interstitial in case of steel, their diffusion rate is higher. And therefore, the solute atoms, this kind of interstitial solute atoms, can quickly move and catch and log the dislocations. On the other hand, in case of aluminium alloys, since these are substitutional solute atoms, their diffusion rate is lower compared to the interstitial solute atoms. And therefore, it will take some time for these solute atoms to reach to the dislocations and log them. And as a result of that, there is a time delay, or there is a critical strain rather, at which the serrated flow will start. Okay. That is because of the fact that the diffusion rate of substitutional solute atoms is lower. Okay. So that is the characteristics number 6, which is about a critical strain which is required to start the serrated flow. So what I mean to say, you can see it from this diagram again, from the stress strain diagram. That only at a particular strain after yielding, this serrations will start. Okay. So this is the strain that we are talking about. So this is the critical strain, which we can denote as epsilon C. And the characteristics number 6 also talks about how it varies with temperature and strain rate. So as the temperature increases, this onset strain or the critical strain epsilon C will decrease. This is because of the fact that as the temperature is increased, the diffusion rate of the solute atoms will increase, because diffusion is a thermally activated phenomena. So as you increase the temperature, these solute atoms will move faster, will diffuse faster, and as a result of that, they can catch up with the dislocations faster, and therefore the serrated flow will start early. So we can say that as you increase the temperature, the onset strain or the critical strain will decrease, right? It can start at a lower strain if you compare two temperatures, one at a lower and another at a higher level. So that can be again shown from here. So if this is T1 and this is T2, where T2 is greater than T1, then you can see that at T2, the onset strain is lower compared to T1, right? That is because of the fact that, as I said, as you increase the temperature, the diffusion of the solute atoms will become faster. So they will be able to catch up with the dislocations quickly. And number 7 talks about the relationship between this onset strain and the strain rate. This will decrease, the onset strain will decrease with decreasing strain rate. So this can be again understood from a simple logic like how we discussed for the temperature. So here when you decrease the strain rate, that essentially means that you are actually decreasing the rate of deformation, or in other words, you are slowing down the dislocations, right? So as the deformation rate decreases, the velocity of dislocation movement will also decrease, and as a result of that, the solute atoms will be able to catch up with the dislocations quicker, and as a result of that, the onset strain will decrease as you decrease the strain rate. Okay, so that can be again shown in this stress strain diagram. So let's say this is at strain rate epsilon dot 1 and the lower one is at epsilon dot 2. And epsilon dot 1 is lower than epsilon dot 2. Okay, so since the strain rate is lower, the critical strain at which the serrated flow starts, that is also lower, as you could see from here, from this point, right? So it is here for epsilon dot 1 at this point compared to this point, which is at a higher strain corresponding to epsilon dot 2. Okay, and with that we come to the end of this particular lecture, but there is more to come on this topic. Keep watching.